All right. So let us begin. Today we are going to move on with the topic from the last time. We are going to move on from the last time. Remember, we finished introducing the Laplace transform, right? And we learned that is kind of like the last representation that we're going to have in the course. So we now know about ODEs, ordinary differential equations. We know about state space. Now we have the last one, which is Laplace transform. All right. But we didn't know exactly what it was good for. So today I show you just a little bit of the properties of the Laplace transform. Not even so much the properties as kind of like a use case of a Laplace transform. And as we do it, as we discuss this use case, I think it will be a little bit more clear why people like, at least used to like to use it. Right, and at the end of the lecture, we'll see one additional tool in our tool belt as opposed to what we had before. All right, so let's begin. We'll discuss the frequency response and Bode plot. Right. So what is frequency response? So the frequency response is a steady state output of the system given sinusoidal input, right? So what do we mean by that? What is a steady state output given the sinusoidal input? Well, steady state here means the output at the time that it approaches infinity. So if given that the system stabilized, saying that something is steady state for unstable system doesn't make a lot of sense. So we usually assume that the system stabilizes, right? After all the transient processes are over, so transient meaning transitional, right? Like the processes that had to happen before we could achieve the final unchanging behavior of the system. After all this is over, you can think about it as kind of like you throw a stone in the lake, and the transient process are all the ripples. Eventually, they're going to die down. That is when the transient process are over, and the new steady state is reached. So the new level of the lake, a little bit higher, is reached. Right. So the response is a steady state output. So output that that comes after all the transient process over. For the system given sinusoidal input. So with stability, we discussed just the behavior of the system relative to the initial conditions. Here, when we were talking about inputs instability, we were either saying there's nothing to say, right? These stability tools have been developed for the systems that are autonomous, right? The tools that we use were developed for the systems that are autonomous. Autonomous implies no input. Or we were saying, okay, if we have an input u, how about we replace it with u equals to minus kx, so controller, linear controller, and then we analyze stability of the closed loop system, so stability of a minus bk. Okay. Okay. So we were saying dx dt is equal to ax plus bu. That is difficult to analyze. So instead of analyzing that, we would analyze something equivalent. but with the use of we will analyze a closed loop system of this type. A means vk x. And how did we get there? We got there by assuming that u is equal to minus a x. All right. So this was our approach so far with respect to inputs. We were saying, okay, this is difficult to analyze, but this is what we can do. Replace the input with the expression for the input and achieve a new closed loop formulation that is autonomous system that we can analyze. Okay. Here, what we are saying is that we don't need to get rid of the input. Input is okay. In fact, we are going to want the input u to be sinusoidal. So we're going to have so this we're going to have here a sinusoidal input. Right, and this is a steady state solution. So a tall order, you can say, we have a linear system. We have to analyze how it behaves, but not now, immediately, the way we would have analyzed if we were trying to solve this equation. So if we are trying to solve this equation, what we would get is just the behavior immediately, right now, right? Instead, what I am asking is, let's analyze how it behaves after all the transients are over, so somewhere at infinity. And we're only interested in how it reacts to sinusoidal inputs. And yeah, that's it. So interesting. Now, before we move on to how this is done, you already saw right now like how it is different from stability. Stability, again, just to iterate, is how we go from initial conditions forward. If it is stable, we contract and approach some solution, especially if it is asymptotically stable. We asymptotically approach some particular solution, some value, right, from any initial condition, if it is a linear system. Right, here we don't say anything about approaching some particular initial condition. In fact, if you remember how differential equations react when you put a sinusoid as an input, sinusoid is going to be a steady state solution as an output. So especially it's true for stable equations. Stable means that exponential has a negative power. So this is not going to converge anywhere. This is not going to converge anywhere. What we are asking, in fact, is if we put a sinusoid here, what kind of sinusoid will go out of here, right? What kind of x will be a sinusoid as well at a steady state. What we are asking is if we give a sinusoid with a certain amplitude and phase, what kind of sinusoid with amplitude and phase we will get out. So that is the kind of discussion we can have with ODEs. Okay. So this was going on. All right. So now let us try to approach this and try to see how we can try to solve it. We could try to solve it with our ordinary differential equation tools, of course. Also, we can try to solve it using our new Laplace tools. So that's what we are going to do. So our equations can be rewritten in this form. Y equal to G times U. any ODE can be rewritten this way. Y is the Laplace transform of the output, U is the Laplace transform of the input, and this in the middle is a transfer function, G. Right? So we have input, transfer function transforms it into output. Okay. Now, sinusoidal input, something like this, U of t is equal to sine omega t, this is the sinusoid with the frequency omega in time domain, can be transformed to a Laplace domain. Remember, we use a convolutional integral for that. Use this integral form. That becomes something that we show here. I'm not going to show how it is derived, just this is how it looks when you transform the sinusoid into Laplace domain. So, given this sinusoidal input, the system then becomes what we showed here. So y of c equal to g of c times omega divided by omega squared plus c squared. So this is what you know, our system, our output signals becomes under this sinusoidal input. Right. What is interesting that here we can say, if we can analyze how this behaves for different omegas, then we can pretty much analyze what's going to happen with this, you know, what's going to happen with this output. And if since we're on steady state, we could try to get rid of everything that is transient, and then we would hopefully achieve the answer. So what we wanted, like steady state response to sinusoidal input. Right. So our game is going to be to try to make sure that this represents steady state part. Right now it represents everything, transient part and steady state part. So what we want to is to kind of want to go to steady state, and we already managed to get the frequency response part here, because this is the sinusoid with frequency omega. Notice we could have done the same thing with ODEs. We could have written ODE, then write explicitly solution to the ODE, and then write explicitly how from the solution of the ODE follows how it behaves under different frequencies of inputs. It would have been possible, but we are trying to do it with Laplace. Explicit solution of ODEs, you can imagine, it would have involved some integration, so also going to be pretty. Okay, so we're doing it here in Laplace. Now, I'm going to just show you a few steps. I'm not going to give you all the steps because there are quite a few. Actually looked it up for a course where this is done carefully. This takes about 4 lectures to complete. So we don't have time to devote 4 lectures to this process. So we're going to do it relatively faster. Right. Now, there is this tool when we discuss transfer functions, which is called fractional expansion. This tool is extremely useful in Laplace transform, especially in the cases when you want to use the Laplace transform to solve ODE. And essentially what we are trying to do right now is kind of close to it. We are trying to kind of solve ODE. Kind of trying to solve Auxin differential equation in order to understand its behavior at the steady state. Right. So when the transfer function is a rational fraction, it can often be represented in this way. By a rational fraction, I mean there's a polynomial at the numerator, polynomial at the denominator. So we can often represent it in this way, where those p sub I are roots of the denominator, you can say. They are called poles of the transfer function. By the way, here of course, you could like this plus sign, you could choose to put a minus sign here, and so on. Here I just follow convention for one particular set of slides, which I'm trying to condense here. So this plus signs here, you can think of it as a convention, but personally find it very useful. All right, so the PIs are poles of the transfer function. What are poles? Poles are roots of the denominator. So polynomial that is here, as any other polynomial, it will have roots. If we write them as complex numbers, and roots of any polynomial can be written as complex numbers. In fact, this is a complex polynomial, so S and PI here can be complex numbers. So you could decompose it this way. In fact, sometimes a polynomial can have strictly rational roots, and then you could write the same thing, the same decomposition strictly in rational, or let's say real roots. So you could write the same decomposition strictly in real numbers. And I think you can probably remember this as a familiar thing. So let me just give an example. You can totally remember something like this as a example of a polynomial of the second degree, right? This would be x squared minus 5x, I believe, right? Plus 6. Something like that. No? So you can see this particular polynomial has an expansion where we, instead of x squared minus 5x plus 6, can write it as x minus 2 times x minus 3. Same here. Here, this is more traditional because the minus signs, it makes it clear what's going on. Here is a plus sign, so it is just a little bit weird to look at. But yeah. All right. Now, especially when p's are real and non-repeating, so not complex, but real, we can expand this whole thing. So we can expand this whole fraction as a sum of simpler fractions. So this can be expanded as the sum of simpler fractions. How do we do this? Well, you can imagine, in order to expand it like this, you would have to consider the right-hand side here. make it back into a single polynomial. So multiply, for example, s plus p1 by s plus p2, s plus p3, etc. on both the numerator and denominator. You have some expression here. Do the same here, do the same here, everywhere. And then collect the terms with the same powers, and then you get something like the solution for what R1, R2, and Rn should be in order for this equality to hold. Right? So there will be a process how to achieve this expansion, but that is not the point. We are not going to try to do it by hand, so don't worry. You don't have to learn how to make the fraction expansions, but just take it to your notice. Can be done for some transfer functions. There is a more general way to do it for all transfer functions, all rational fraction transfer functions. I'm just trying not to go into the deep end of this whole thing, and trying to keep it simple. So for particular cases, such as this, we can do this. All right. The results are general. I'm just giving simple examples of what's going on. Right. So what's going on is we have a transfer function for which we can rewrite it in this way. We went from here to here, now to here. If we knew g of s, we know everything about this one. Good. Now, in our case, we have something more. We have g of s times this sinusoidal input. G of s times sinusoidal input expands something like this, where we have here this expansion that has to do with the poles of this guy. So those particular values p has to do with the poles of this transfer function. And this here is due to this addition. So those two components have to do with the fact that we had this additional input. Where does this come from? Well, you can kind of look at it and recognize that this is just the roots of this denominator here. So that's why we have two addition terms. They're just roots of this denominator. Okay, so we have this new fractional expansion here. And this now represents the functions that we want to study to get this sinusoidal steady state response. Now, this guy, so like any one of those guys here, we can do inverse Laplace transform, or just recognize how this guy is made. Right, it is made from an ODE. We can go back to ODE. It will be first order ODE, and essentially what we can do is we can just solve it. Okay, we can just solve it for zero initial conditions. And with Laplace transforms, we usually work with zero initial conditions. We get solution of this ODE corresponding to this transfer function. Or if you want, we just have inverse Laplace transform of this transfer function that looks like this. So we could just plug it directly into the integral for inverse Laplace transform, and we will get with this guy. If you look at it carefully, I think the argument that we can do it as a inverse Laplace transform is very powerful argument, but the only problem is it kind of loses reality a little bit. When they say, oh, this is a Laplace transform of the sinusoid, you can kind of like be like, okay, whatever. When I say, oh, this is inverse Laplace transform, you again kind of like whatever. But here you don't have to be whatever. You can just see what's going on. And what's going on here is that this is just a solution to the first order ODE, which we know very well. Here is the eigenvalue of this, system. It happens to be negative pi. Here, this is a like what normally occupies the role of the initial condition, RE. So usually this is the initial value of y that stands here. So that's it. That is it. That's what we have here. Okay. So this is what we get when we transform something like this back into time domain. Now, for a stable transfer function, where p in this formulation would be positive, this part would be negative. So this whole thing will go to 0 as time goes on. So this whole thing will approach 0, okay, as time goes to infinity. So this whole thing is transient. That is kind of like the whole point of doing this decomposition, was to see that this part is going to be a transient. What we didn't do is we didn't do the same for general case, but in general, you would also see that we would have those parts for a stable transfer function. All those parts are going to go to 0. And you can totally imagine how you would do the same argument in ODE form. You would write explicit solution of the ODE, and then recognize that some part of it is going to 0 because exponentials, same as here, have negative powers. Because for stable systems, eigenvalues are negative, have negative real parts. And what we are left with is whatever does not go to 0 at infinity, namely those guys. They're not going to 0 at infinity. That is a steady state. They would represent steady state response of the system given the sinusoidal input. If we did it in ODE format, we would have had to deal with the fact that we have an integral over something else, we have state transition matrix, etc. So the math wouldn't be much simpler, is what I'm trying to say. Here it is not very clear, because the Laplace transform, I think it is a little bit less clear than working directly with state space. But at least it is simple. The math, if we did with matrices, would have been more complicated. All right, but you can do it in both ways. Okay. Now we have this understanding that what we wanted to study is essentially how this part behaves. Okay. The next steps, and here we're not going to go into minutiae of the algebra, so we're going to skip right to the solution. But the next steps would be identify, if we try to do it rigorously, especially, identify what alpha and beta are. This comes from fractional expansion. So we need to identify what they are in terms of everything else. That's the first step. Next step, convert it into time domain, which will be quite easy. We know how those things behave in time domain. And by the way, notice it is no longer going to be, convert it into the time domain. Next, we would want to see how in time domain, the solution time domain is going to be a sinusoid, right? So how in time domain the amplitude of the sinusoid changed, and how the phase of the sinusoid changed. Okay, that is what we are going to try to understand, and we would find explicit formula for that. But we are going to skip this part of the derivation. So far, what I want to show you is what happens with the transfer function here, and that we have this part that goes to 0, this part remaining. All right. That is just kind of like for to see what's going on. Now, one last observation is that when we are going to look for those alpha and beta, what we'll find is that they depend on the value of the transfer function if we substitute g omega there. I'm not proving this, it's just giving you some information. We would have transfer function where instead of s, we substitute g omega. And that's how we'll find alpha and beta. Okay. We could just write it out, and that's what we're going to see, but I'm going to skip this part. So somehow we can use our transfer function, but just substitute different variable. So delete essentially the real part of the s. S, remember, is a complex variable. This s is a complex variable. We delete real part, only keep the imaginary part, j omega. We can denote the imaginary part as well, and we get the expression for alpha and beta. Okay. Now, okay, so far so good. Now I'll try to take a pause with this math barrage and try to approach the same kind of reasoning, but just from a different angle. And then we would get to the solution. All right. So remember, last lecture, I was talking a little bit about the relations between different transforms: Fourier series, Fourier transform, Laplace transform. So remember what we were saying. Fourier series represents a periodic function as a sum of harmonics, sines and cosines. Okay? Those harmonics form a basis in the linear space. Coefficients of this decomposition like a discrete spectrum of the function. So the function, its spectrum, can be seen as having discrete points there. Yeah. Spectrum means what kind of frequencies you have to sum up to get the original function. Right. Now, Fourier transform gives a continuous spectrum. It does essentially the same thing, but it gives a continuous spectrum of the function. We no longer speak about periodic functions. This is true for all functions, periodic or non-periodic. The basis is still made out of harmonic functions. Finally, Laplace transform with continuous spectrum, but the basis is no longer periodic sines. In fact, the basis is now given us exponentials. So it's solutions to the first order ODEs. It is those second order ODEs. Sorry. It is those dying down exponentials. It is sinusoids. It is just exponentials without sinusoids, and so on. Dying down sinusoids, etc. All of those things. That's how you can think about Laplace transform. So it is a more general form, right? So Fourier, remember, just sinusoids, Laplace, sinusoids, exponentials, and sinusoids that die down exponentially. So all types of solutions to ODEs. Okay. And we can even see the similarity in mathematics directly. So here is the Fourier transform. We have original function. Here is the Laplace transform. We have original function. Here is a transform of the function in both cases. This is a decision variable. We use a small font. So this is a decision variable in both cases. Here omega is a real number. Here's S is a complex number. Okay. We see in both cases we do integration over dt. In both cases we have e to the power of something, okay, including t here. And the integration goes from minus, here it is from 0 to infinity, here it's from minus infinity to plus infinity. But this technicality you can avoid if you do double-sided Laplace. We're not going to talk about it, but essentially you can think of this as a technicality. In this case, at least, for this discussion. Right. So the main difference is directly seen in how here we have 2p j times omega. This is a 2 pi is just a coefficient. J is a complex square root of -1, so complex one. And omega is complex value. So this whole thing is just complex number that can be anything. This omega here goes directly here. So this complex number here goes directly here, but this variable here is not complex, it is real. Right. Here we have the same situation almost, but we have S, which is a full-blown complex number. So omega is still real, it is just multiplied by a complex j. Here S is a complex number. And if you remember how exponentials work, e to the power, let's say, how should we write it? Al to the power a plus jb. Okay. So this is a exponential, with j being exponential. Would be equal to e to the power a times e to the power jb. This is how exponential works. This is how powers work in J. If you have e to the power something plus something, it's the same as e to the power something times e to the power something. This becomes this. This becomes this. So in the same, and then this part here, let me choose a different color. This part here, you can see it is totally here, right? Let me try to clear something. It is totally here. Right. That's it. That is the complex part of the complex number, or e to the complex number. This, on the other hand, this on the other hand is this guy. So the difference between Fourier and Laplace is that we are missing this component. We are missing this part, e to the power a. So we are missing the real part of the complex variable in the Fourier transform. In the Laplace we have it, in the Fourier we don't. But for the system which represents a stable differential equation, you can mention that this part is going to be dying down exponentially. So this is in fact what represents those transient responses, so the responses that are going to die down. So somehow you can kind of see that the difference between Laplace and Fourier is that Laplace, in terms of solutions to equations, Laplace cares about transient response. Fourier doesn't. So we have this difference. Okay? This is just, blah, blah, blah philosophy. You should be concrete with math when you do this kind of stuff. But all I'm trying to say is that somehow it makes sense, if we are going to go to transient responses, to forget about variable c and go back to the variable j omega. Okay? Because what we lose is exactly what we don't want to see in this analysis. All right. So this is the same what I was just saying, just pointing out. So when you saw study, you can go through this text on your own. This kernel that we left. So let me. So this is our Laplace variable. If we get rid of the real part, what we get is when we go look at the kernel is e to the power minus g omega t, which is the same as cosine omega t minus g sine omega t. So you can see it is this kernel becomes just a harmonic function. So it becomes very similar to Fourier kernel. Right. So the idea of a Bode plot will be to take a transfer function achieved with Laplace transform and replace S variable, which is a variable needed for Laplace style reasoning, and just replace it with G omega. So it's the Fourier style variable. So somehow we're going to get this way. We're somehow going to get rid of the transient part of the transformation. And to my mind, this is kind of like one of the reasons why people used this so much, because in the era before computers, you could do this, math, which allows you to deal with the differential equations as fractions, expand them, solve them by using tables. Essentially, like inverse Laplace transform, you can do it. Just look up table. And you could even do this analysis of the steady state solutions without doing any matrix algebra, as you would if you would want to do it with the state space equations. All right, so we just mechanically replace this with this. And then instead of transfer function of C, we would analyze transfer function of G omega. Okay. Now, what we would want to do is then with this transfer function is plot its amplitude, which is the absolute value of this transfer function. Remember, it is a complex number. So absolute value of the complex number, there is a formula for that, right? It's like a sum of the real part plus imaginary part squared. And we would analyze the phase. The phase is, I've just given you a formula here. So it is the angle between the imaginary part and the real part, like given arctangents. If you want to find what is good definition of the angle of imaginary number, you can just go on Wikipedia or anywhere else. Here, just give you explicit formula how to compute it. With A10, A tangent to arc tangent to, okay, that's what's it called, quadrant tangent. That good definition would include just normal arc tangent, but of course, if you're going to use it on a computer, you better use a tangent to, okay, to avoid some problems. Right. So this is what you want to what we're going to study. This is essentially how the system is going to react in terms of increasing or decreasing in magnitude. So you pass a sinusoid through the system. How the sinusoid is increasing or decreasing, that is what this will tell us. And second, we pass the sinusoid through the system, and the sinusoid shifts by a little bit. This guy is going to tell us the situation. Now, Bode plot traditionally includes very specific ways of plotting those things. First, we don't plot A. Instead of plotting A, we plot 20 times log of A. If you weren't prepared for crazy things happening all the time, you would have probably not been happy about seeing this. It's not here, because what is 20 times log of A? Why? Okay. Log, you can kind of understand why, probably, because otherwise the graphic is going to be dominated by some frequencies. You want to kind of like squish it down. Log makes the vertical axis to become more kind of like easy to read, I guess. If you ever try to plot stuff where you have some aspects dominating everything else, you probably try to replot as semilog. That's what we call those graphs now in at least computer graphics, semilog. So where one axis is logarithmic. In fact, I'm pretty sure we're going to plot both axes here logarithmically. But anyway, yep. So this is just to make it easier for the eye. And 20 here is kind of interesting. 20 here has to do with the fact that we are working with decibels. Deci means 1/10, 1/10. Yep. So this is how we get 10 out of here. And 20, this 2, has to do with the fact that originally those plots were designed for not plots even, but originally people wanted to work with energy, which is a square of amplitude. So if you want to go back to amplitude from the energy, you would want to, the relations is by square. And the square going through the log gives you 2. Okay. If you go put this 2 back under the log function, if you take exponent, I guess, out of this whole thing, you'll get something squared. Okay. That is where 20 comes from. Like the 2 comes from the fact that we originally wanted to work with energies, and there you have squares, and the 10 comes from decibels, which are 1/10 of a bell, which is something you don't use. We only use decibels. All right. Anyway, it's just a convention. If you don't plot it as this, nothing will happen. It's just convention to plot it this way. Okay. Now this graph here, we plotted as in degrees, basically, not in radians. So you have to remember to multiply it by 180 over pi. Okay. Good. So we are going to plot those two plots, one in decibels, the upper one, the low one in degrees. Okay. Let us try to do an example by hand. Here is an example of a pretty simple transfer function. 1 over 1 plus c. Let us try to plot Bode plot for it. At least prepare the functions to plot a Bode plot. We substitute instead of we'll try to be careful. Instead of c, we substitute j omega. So instead of c here, we have j omega here. Okay. Now, in order to write it in like in a simpler form, we're going to multiply both sides by, let me do some other color, by I minus j omega. Multiply both sides by that number. And we get this expression here. Just making it a little bit easier to work with. Why do we need that? Well, it's a little bit hard, at least for me, to compute complex part and the real part of a number where complex number is in the denominator. Like I just don't know how to deal with this very effectively. Whereas for this guy, we can clearly see that there is a real part here and the complex part here, right? So we know how to divide it with one part. In fact, here's the real part. Here's the imaginary part. So I was using complex imaginary part. Imagine. Here's the imaginary part. All right. So Bode plot is then given us the following. So first we need to find absolute value. The absolute value is of this number. It will be this squared plus this squared, square root. So you can see here 1 squared from here omega squared from here, and the denominator is being squared. When we open the, we can see the denominator and the numerator contain the same value, so we can get rid of this thing and this thing, and we obtain our final solution here. This is the amplitude plot. But remember, we would have to take the logarithm of this guy, multiplied by 20. Here you can instantly see that logarithm will make our life easier, because 1 plus omega squared is going to be is now to the power of minus 1/2. This minus 1/2 could go in front of the logarithm or something. So logarithms of these types of functions are nice if we're going to do it, but we're going to plug the computer anyway, so it doesn't matter. Okay, now to the phase part. Here it is even simpler, since we are not going to simplify. We just take directly the imaginary part, put it in our arctangents 2. Real part, put it in our arctangents 2. Done. Yep. So you could, of course, try to, simplify it further. You see that those are ripe for some further analysis, but if I'm going to pull it to the computer, it doesn't matter. In fact, people develop a whole lot of techniques for plotting Bode plots without computer, but we don't have to. So let's just use the computer. Right. So before we discuss how to analyze a Bode plot, let me remind you of the last lecture, the last slides. So remember closed loop transfer function with when the feedback law is very simple. In fact, when it is identity, it would look something like this. So this is how transfer function looks. Now we can do Bode analysis on it, Bode plot analysis. So we substitute ij instead of s here. What we get is this expression. And we see that this guy will become badly defined, or will just explode when this guy approaches -1. Why? Well, because we have 1 here. If this becomes -1, the denominator becomes 0. Bad things happen. In fact, what we can say in this case is that the system will stop being stable. Even if it was stable originally, it wouldn't be able to, how should I put it? It wouldn't behave well. I guess that would be a mild way to put it. So what we want to avoid is putting the system in this situation where this guy becomes -1, because then the transfer function here is not going to do anything good. And that is one reason why we want to do Bode analysis, even for stable systems, because there are frequencies on which this can become -1, and the system can fall apart. Maybe you know the famous story about the bridge which collapsed under vibrations of a marching army, right? Is a famous, I think, old world story. I'm not sure from which century it is. Hope that I don't know what I hope, but it's kind of like you wouldn't want to think that it's 20th century, but essentially you had a bridge, and a lot of people were marching, kind of like simultaneously beating with the feet, and the bridge started to oscillate. It went into resonance, and then it collapsed. Okay. There's a famous story. People on what call it? In the classes where you study resonances, you habitually tell the story as a reason why you need to study resonance behaviors. So here, this is kind of like that, resonance behaviors. Your system may be perfectly stable. Bridge was stable, like push it a little bit down, it will go back up. Stable by Lyapunov stable. Okay. From any initial conditions, it goes back up. But it wasn't designed for specific frequencies that it was put on it. So some specific frequency was managed to oscillate it, pump energy into it, and to make it unstable. In fact, we have those analysis tools outside of control theory, which just specifically deal with this kind of behaviors, trying to understand when the system will resonate, to which frequency it resonates, and so on. All right. So what we want to avoid is to making this part to be -1. Otherwise, the transfer function seems to approach infinity. And this is not something we want to see. All right. So let's see how it works. Now, before we see just one thing, what does that mean for this function to approach -1? Well, this is a complex number. This is a complex number. It can be just -1. That is a possibility. It can be just -1. Another possibility is that it is equal to 1 in terms of, when we represent in terms of polar coordinates, it is equal to 1 in polar coordinates, as in the length of this number is 1. And the phase, so the angle, is -180 degrees. Okay. So on imaginary plane, 0 degrees represent a purely real number, 90 degrees represent a purely imaginary number, 180 purely negative real number. Okay. So just to quickly illustrate, on complex plane, we have purely real numbers here, and the phase is 0. Here of purely imaginary numbers, phases 90 degrees. Here purely real but negative, phases 180 degrees. Okay, everything between is of course. Okay. So what we want to watch out for is amplitude of 1 and phase 180. Right. So here we would have illustration. Let me see if it works. Yep, it does. So this is a website you can visit it on your own and just look at it. But I really like these pictures that it produced. So this is how Bode plot can look like. This is a magnitude part of the Bode plot. This is a phase part of the Bode plot. This is in decibels. This is in degrees. So let us look for danger signals here. So all right. A logarithm of 1. So we want to look for when the amplitude becomes 1. What is a logarithm of 1? Well, to which power do we need to raise e to get 1? Well, to the power 0. So what we want is this graph. We want to look for 0. So this is a dangerous part here. Well, this whole line is dangerous. We want to see where the graph crosses it. In fact, it crosses it here. So this is what we call gain crossover frequency. So this is where gain is, we talk about it as amplitude, but we cannot talk about it as gain, as in how much it gains, how much it increases after, the output of the system increases as compared to the input. So you see, here you can say that the amplitude crosses this dangerous line. Okay, good. That's what happens in this part. We have to really hope that at this same frequency, so if we go down, at the same frequency, we don't have at the same time phase plot to be at -80 degrees. In fact, at this frequency, the plot is a little bit below 180 degrees. So we're safe. We're not in danger. But let us study how far we are from it. And you can see that we only have this tiny difference. So only this much difference between the phase and this point where we would collapse. Okay. The way people think about it is this. they'll say, how much can we shift the whole graph up and down before it collapses? And here we have like just a few degrees that we can use to shift it up and down. Okay. We cannot shift it, a lot before we are in danger. So we have very little amount of margin. And, we can call this, what I showed here, a phase margin. So if we are going to change something about the system, there's just a little bit and the phase will go away. All right. Now, let us do the same exercise, but with, let me see if I can somehow show everything. Yeah, phase margin. Now, let us do the same exercise, but now we would look at our frequencies, So the dangerous frequency is this one. Sorry, frequencies. What I'm talking about? Phases. The dangerous phases are 180 degrees. Okay, this is the dangerous part. 180. So we want to make sure that we do not that when we cross this line, we cross it in two places. For example, here, another one is here. That at this point, so here is a dangerous point. Right? We don't have corresponding situation where the gain margin is 0. So we go from here to here, and we notice that actually we are at the gain 20 decibels. So the gain margin is 20 decibels, right? 20 decibels. All right. So if this guy moves here by 20 decibels, so for example, your controller is being tweaked and your Bode plot kind of shifts down, you have quite a bit of shifting before you cross this line. We have basically here another place where we go across 180. We could try to do the same exercise here. And we'll notice that here the amount of the amount of leeway we have is much less. So it is not enough to say, oh, here everything is fine. We can also look at it here, and it will be different story. So while we can shift down 20 decibels until we become unstable, if we shift up for just a few decibels here, we will also become unstable because of this part. Okay. So this is a way we could analyze it. This is the way we could analyze it. Of course, if both of those shifts happen at the same time, which is actually very typical, we could be in trouble. Our analysis here somehow separates them, but in practice they're not separated. So we could do some other analysis tool like Nyquist plot, etc. I'm not going to discuss all of those individually, but Nyquist plot is the most popular ones we didn't discuss, where you could try to do it at the same time, basically analyze at the same time what's going on, and I see your distance to this dangerous point, 0 minus 80. Okay, but the point of this diagram is not just that. It is also just to see how your system reacts to various frequencies. So you can see, for example, here is the system for frequencies until here. The system kind of amplifies. The frequencies from here, it kind of dampens them. Frequencies here, different behavior for different frequency. Here you can see that for those frequencies, it introduces you could say a lag of 130 degrees or so. Here, in fact, like the signal becomes almost kind of like opposite of the input at those points. And here it goes a little bit beyond that. So you could try to use it to analyze how your system is going to behave. That's what I'm trying to say. And concluding that your system is stable does not imply that this analysis is going to work out well too. Because here, again, what you are discussing is how much you can push your system until it stops responding to particular frequencies, until some frequency will be able to destroy your system. Okay. So this is a different story from stability. All right. Now let me see if I can go back. Okay. Okay. Now, you could do the same thing in Colab. I provided an example. The link to this example is in the slides, where you could do all of this in using Google Colab. So, for example, if you have a transfer function represented this way, you could just instantly do Bode plot. That is the beauty of modern age, where we have computers. Just do Bode plot like this. Not as pretty as in the website that we just watched, but you can try to do analysis. Here it's not very dramatic. It is never zero. Like it approaches zero, but only at the lowest frequencies. And minus 180 is never achieved. So stable for all frequencies. Infinite margin, we sometimes say. Right. Now, we could do the same thing as we did in the slides. So, for example, we can define, here is our real part of our transfer function. When we substitute G omega, here's our imaginary part. Then we can just go through all frequencies from what spectrum we go. We define spectrum. Okay, so the same spectrum as we got from here, but you could just define your own distribution of frequencies. So for each frequency, you get the real imaginary part of this transfer function. Then you get your amplitude plot like this. Yeah, by the way, this is log 10, not log 10. It's a log base of 10. But in terms of our discussion of 1, so 10 to the power of 0 is 1, same as e to the power of 0 is 1. So the 0.1 is the same for pieces. So we have this, I think, directly kind of like in the slides. The squared there, decibels, and here atan 2 from this, and multiply by 180 divided by p5, and we plot it as semi-log x, and we get the same exact results. So nothing mysterious about Bode plot. I think like Bode plot traditionally in engineering colleges we just do this part, and we are happy, and we often do it in Simulink, so we don't even see the code. And this is kind of like how we often introduce to Bode plot. I think it is nice to be able to see that it is actually extremely simple. Like, you know, this is the entirety of math after you're done with substituting to the transfer function, right? The transfer function, sure, it is a little bit of work to substitute, but if you know symbolic math, you can do substitution automatically in your code, and you essentially won't have any work to do. So it's not so difficult to plot a Bode plot. And it's not nearly as popular instrument of analysis as eigenvalue stability, because often enough we don't discuss reaction of the system to the input. But you have to think about it, right? If you're going to control your drone, for example, or your robot, you're going to give it inputs which are going to have different frequencies. And if you want your drone or whatever, your autonomous car to be stable, you have to be able to show that the frequencies you're going to give it are not going to lead it to crash. And for that, you have to use Bode plot, not eigenvalue analysis. Eigenvalue analysis is like step one. If your eigenvalues are unstable, your drone doesn't have a lot of chances to even, be useful. But if your Bode plot tells you that you are very close to being unstable, and some small variations can push you towards instability, well, that is maybe not as bad, but close enough. Because, in practice, you're going to give it frequencies with your commands, and you don't want those frequencies to drive the system into instability. So for practical reasons, for us, people who do robotics, this is of high importance. Even if you're not going to use it every day, maybe you look at it, you say, okay, Laplace, okay, imaginary numbers, the mathematics requires some kind of fractional expansion, inverse Laplace, blah, blah, all of this too much. You would say too much. I'm going to be a simple person. I'm only going to use eigenvalues. Fair enough. A lot of us only use eigenvalues for analyzing our systems. But as soon as you're going to seriously work on something that involves inputs, you have to start thinking about how those inputs affect your stability. And here you have to remember that your inputs affect your stability separately from what we discussed in asymptotic stability, etc. So like reaction to transient responses to eigenvalues, like where do they land? Where do those final like trajectories land? This is a separate matter which you have to study additionally to your eigenvalues. And a lot of modern control explicitly focuses on steady-state response or worst-case scenario response, etc., to inputs. So this is not quaint, antiquated stuff. This is just a different problem, closer to reality, slightly more difficult. So that's what I want you to keep in mind. Right. I think this is it for what I wanted to show you. Do we have questions?
I think no.
I mean, I can understand. Bode lectures are somehow, especially again, this is like a condensed version of 4 lectures or 5 lectures on a normal course. I understand that this is much. This is much. The only consolation I can give you is that the mathematics is this, and this is, get rid of plot, and you get 2 lines here essentially, and this, which was a 1 slide. Math is not so difficult here, but conceptually it is quite difficult. But nothing here that cannot be done with your mathematical background. So don't worry about it. I understand that it sounds scary, but it is not very scary. Right.
Also,
Yes.
I know that there is we can write complex numbers in Python. Can we use it here?
We can.
Like it seems like just using like tuples to define it, not like exact complex number.
Yeah, so what you propose is we write a exact transfer function with complex parts, with complex numbers, substitute omega there, and then just get out a real and imaginary part as using some built-in Python functionality, right? Yeah,
Yeah.
we can totally do it. I wanted to keep it as simple as possible, this one, but yeah, of course. And in fact, all manipulations with transfer functions can also be done with symbolic math or with something else. There are also built-in tools. Like this is not so bad either. Like those 2 lines, nothing bad here. You can just do it this way as well. So it's just important to kind of like understand what is behind there. But once you are comfortable, this is perfectly good. If you're going to analyze your system for, let's say, some project, 2 lines, and you don't know transfer function, often enough, what you can do is get your state space matrices, write something like state space to TF, and you get your transfer function from there, and you can do Bode immediately. So, yeah, of course, do everything. Is there's no, this is actually simple. It is just a lot of concepts, but the math is simple.
Yeah, I see.
No, thank you for the question. It's a very good point. Right, then we're stopping here, and we'll see each other next week. We'll soon be done with this part of the course where we do the beginning like analysis, basic ideas of control design, stability, and we'll have a midterm. After that, we're going to go to the second half where we would have a little bit more tools, etc. Like analysis part is going to be toned down a little bit more. I mean, here we mostly did analysis, representations, etc. And we're going to see more practical stuff, immediately useful and so on. All right, we'll see each other.
Okay.
Bye.
Bye.
Goodbye.